I've been doing work recently in myths and misconceptions related to cybersecurity, and I thought I would discuss one of the biggest myths that we don't really understand what cybersecurity is. If we look at characteristics of a common field, and let's think of something like chemistry or medicine or psychology, these fields have a history associated with them. There is an accepted body of knowledge that everyone practicing in the field is generally aware of. Some generally accepted references, books, standards, other things, and common terminology that they use. Now, when those aren't fully developed, we end up having myths and misconceptions and folklore that people fill in to explain what they're using and how they're doing things. And again, to sort of go back and look at chemistry, for instance, very early on, the alchemists, who were the early chemists, talked about finding a philosopher's stone or other kinds of things that now we view as well, I won't say nonsense, but certainly uninformed. And in medicine, going back to the ancient Greeks, talking about the four bodily humors and how they had to be in balance, and that was the cause of disease. So once science advances beyond a certain point, we are able to dispel these myths, but some of them tend to hang around for a while. I'm going to say cybersecurity is not a new field. It is not the same as computing. Cybersecurity involves other things. But we have a history that goes back into the mid-1960s, which is not that long ago when you compare it to other more established disciplines. But one of the very first items describing cybersecurity issues, although not by that name, was the Ware Report, chaired by Willis Ware. Project Multics, that was started a couple of years after that to explore operating system architecture and security issues. The Anderson Report by Jim Anderson, that was a follow-on to the Ware Report. And then an early series defining secure computing systems, the Rainbow series that included what was known as the Orange Book in the US, the Trusted Computer Systems Evaluation Criteria, that came out in '83. And thereafter, similar kinds of standards were issued in other countries. But these are all the early precursors of the field that define that we really did have a history and an organization. Not only that, we have developed over time a number of standard common bodies of knowledge. We also have organizations, government organizations and others, setting standards of behavior and standards of compliance. In the US, NIST created the cybersecurity framework, and that's been widely adopted around the world by a number of countries as a set of controls and standards for how to protect systems. We have international organizations like ISSA and ISE squared, the British Standards Organization, the ISO, all have set various standards relating to cybersecurity practice. So the field is becoming more defined. We also have a number of standard references and textbooks in the area. Matt Bishop's very definitive work on computer security, the textbooks, Flieger, Belevin, Anderson's wonderful security engineering book that he wrote as a professor at Cambridge, William Stalling's books. So we have standard textbooks, and these are used not only for teaching, but as reference items. We also have common terms of art that are peculiar to cybersecurity. For instance, when we talk about a virus, we're not talking about the biological virus. We are talking about something that alters and embeds itself in computer software on our computers. Ransomware is a term of art that does not get used anywhere other than in cybersecurity. When we talk about return-oriented programming, or ROP, that's another term that has become unique to cybersecurity. And we have other terms like side channel and others that are there. So if we look at this set of characteristics, this really matches what I said about defining a field. cybersecurity as a field is becoming more defined over its 60 or so years of existence. And I'll note here that it is much more than just computing, which is why I said it's not really a subset of computing, because it also involves issues of psychology, economics, law, communication theory, and other kinds of issues that are outside the realm of traditional computing. The word cloud I have here actually is related to that. We look at these and we see these as things that are related to cybersecurity, but these terms are all more oriented towards relationships of people and organizations. Well, given all of that context, we can say, okay, cybersecurity is a field, good. Why do we have such problems with it? And I'll say it's because of one myth that we've sort of glossed over with all of this, in the idea that we have a clear definition of cybersecurity. And I'll show you why that really isn't true. And I'll do that sort of walking through some analysis of potential definition. Really, part of it gets to the root of what is security. We use the term security in a lot of ways. We talk about national security, we talk about personal security, data security, and others. If we're in a company and somebody does something wrong, we tell them to call security. But what does it really mean? In the 60s, when some of the experts were doing the initial work and they were analyzing computer security, they realized that it's an unattainable goal. And I'll show you that in a moment. So they then started talking about trusted systems rather than secure systems. The idea of building computers that we could trust to execute according to a policy. Well, that also turned out to be extraordinarily difficult and actually unreachable. And so they switched terms to the idea of trustworthy systems. That lasted for a while, became also difficult to justify, and the terminology changed to the idea of resilient systems. So in the early part of this century, many of the people working in the field started talking about computer system resiliency. Of late, we've now moved away even from that, because that also seems to be a somewhat vague term, and we talk about risk factors, risk reduction, risk abatement. Is this where we'll end up as a definition area? Not sure. But I will say that without a clear definition of cybersecurity or some one of these terms, we can't build appropriate metrics. And without metrics, it's very difficult to determine if some new development, advancement, or configuration is both an improvement and worth the investment. Metrics are critically important for defining any scientific or engineering field and are very important for making progress. It's also the question here about whatever definition we have, how is it related to safety and to privacy? Both are concepts that repeatedly appear whenever we talk about security. So where we are now is basically with folk wisdom, old concepts, and sort of vague notions. Let me give you an example here. If we start with an intuitive definition that a system is secure if it's protected against all forms of threat, that would seem to be what most people would nod their heads at and say, yes, that's a good definition.
I'm nodding away.
Then where does that take us? Well, if we start examining that and we start thinking, can we achieve it? Can we protect against random hackers? Oh, yeah. I think most trained cybersecurity professionals with available tools and technologies can keep the random individuals out of their systems almost all the time. Malware, things like computer viruses and ransomware, probably if you have people who are focused and paying close attention to what's going on. How about nation state hackers? This would be in the area of espionage or conflict. And they're probably not. The countries that are practicing cyber warfare or cyber espionage have a lot of resources and many talented people, and have shown time and again that they're able to penetrate even good resources. So there's an example where our security perhaps isn't quite so good. But it's even worse than that. Can we protect our systems against a UFO invasion? No. Here's a threat picture, a threat model that we don't understand. It hasn't occurred before that we know of. And therefore, we don't know what we need to protect against, what defenses, what indicators and warnings. And so we're effectively not protected at all against something like this.
We could send in Jeff Goldblum, right?
If we had Jeff Goldblum with a properly configured Macintosh, yes.
If we plant a virus into that mothership.
Yeah, but that's exactly it. How about an extinction event meteor impact? Yeah, there's no way that your IT staff is going to protect against that. And that wouldn't be the first priority in any event. If this were to occur, effectively all of our computing resources would be disabled and destroyed, although we wouldn't necessarily have a population who wanted to use them. But you're thinking, how about if we set up some Mars colonies and we send them backup tapes of all our data and our cat videos? Will that preserve them? And well, that's not a bad idea for a number of reasons, but eventually the heat death of the sun, when it expands into a red giant, will consume all of the inner planets, including Mars, and that's the end of that strategy. But if you're, again, sort of thinking ahead here, you sort of say, well, we're not confined to the solar system. Best projections now is that there will be a heat death of the universe eventually, and all computing will come to an end. And in that regard, we've also lost the security battle. What this illustrates is a couple things. First of all, that it's not a helpful definition because we can never actually achieve it. And second, it also shows that security generally is an economics issue more than an engineering task, or at least as part of an engineering task, because engineering requires an investment. And we can build in safeguards of increasing complexity and difficulty of penetration given a threat model. We can never reach 100%. And that the increase in what we have to spend may not be worth what we're protecting. So as a definition of cybersecurity, what I just showed you doesn't really work very well. Let's try a different approach and look at system design rather than protecting an existing system. Can we do something better? Well, research in the 1970s, 1980s, when some of this was originally done, looked at the idea of system state. And any of you who have looked at computing a little more formally know the idea of state. That's the value that's in memory and registers on a system. And if we start off by saying we're going to define a set of states as okay or secure, and we can do that according to a formal model, and I mentioned a couple security models here, Bell LaPadula or BIBA. You don't need to worry about those unless you've studied them. But the idea is that we can have a policy that says what a safe state is. As the system executes, as the computer runs through its instructions, it changes state. It goes from one state to another. And as long as valid operations result in the system still being in one of those allowed states, it's still secure. But that implies, and in truth, there are bad states or unsafe or unsecure states. And those are ones we don't want to occur. We don't want to enter one of those bad states. And we especially don't want to remain in there. So we enter a bad state and stay in operation in that bad state or cease operation entirely. So the notion of allowed states is a match to the concept of system specification in software engineering. The execution of a state that's not in a specification is a fault that can result in a failure. A failure in a protected system is a security failure. And I note that security was a driver in the development of software engineering. But we're not limited to just non-secure and secure states. We also have undefined states, because in a computing system with any appreciable amount of memory, not to mention multiple processors that are involved, we're going to have so many states we can't define all of them, and some of them are undefined. Those are not part of the specification. If program execution enters one of those undefined states, that's an error, and it may or may not be a fault. It could possibly lead to abnormal behavior or a security problem. Some of those undefined states we may enter and they'll lead back to an okay state, but they're undefined, so we don't know. Well, this is what program state space probably really looks like, is we have a small number of specified secure states and a larger set of specified unsafe, unsecure states, but a huge universe of states we have no idea what is going on in those systems. So this is what it would look like if we had specifications. But the problem is that very few bits of software we use have been formally specified. The programs that we download or that we buy from major vendors generally are not specified. They're built according to an informal ad hoc specification, and very often they're modified on the fly without any kind of careful design and consideration for what the system should be. So one of my favorite quotes, a program that's not been specified cannot be incorrect, it can only be surprising. This is the current state of cybersecurity. Really, if we're going to be accurate, most of the behaviors that we say are security problems are not really a failure of design or a failure of building. They're a surprise because the software is behaving in a way that we didn't anticipate. It's a surprise. It's not a good surprise in many cases, but it shouldn't be a surprise because we haven't built the software carefully to begin with. So that's, in summary, a little bit of where we are now with the whole idea of cybersecurity. We have surprises. We don't know how to build systems correctly in the general case, and we don't invest enough to build them correctly, and we don't have the personnel necessary to build them correctly. So we're still searching for that the alchemist stone to try to buy and add on to our systems, or trying to apply leeches to get the systems to behave appropriately. But that isn't really the underlying solution. We have to go back to first principles and do a better job on design. If we do that, if we can come up with that better definition of design, it will help us in future generation of systems, of architecture, of software. It will enhance our communication across disciplines, support development of better tools, and of course, metrics, which will allow us to decide appropriate investment. So all of this requires that we really understand what we're doing and get away from the myths and the misconceptions and the folklore that we've been using up to this point. And with that, I'll say this has been part of an ongoing project where I've worked with some others to try to document some of these myths and misconceptions that we've been applying over the years. And cybersecurity in particular, here's information where you can find out more.
It made me think, actually, the idea of going back to first principles. I mean, it's so complex, isn't it? We've got hardware, we've got operating systems, we've got user experience, we've got software sitting on that. If we're still at the stage of if the witch floats, she's a witch. If she sinks, she's not a witch. Do you see what I'm saying? How do you return to first principles in a system that's already so complicated?
This is related to the economic issue of sunk cost. We have such a huge investment in infrastructure, training, software, that people are loath to throw that out and go back to first principles. Part of what those of us in academia and some industry are doing in research is trying to develop better systems. There's probably not enough attention being paid to that area of research. I've certainly run into issues where talking to people, they're not interested in research for better security unless it works on Linux or Windows on an Intel processor. Well, right there, we've set constraints that may not be appropriate. If we develop something that works better, then demonstrating that in isolated environments is helpful. Now, we do have some better secured systems that are in use in nuclear power, in avionics, in space, but they're expensive. And without good metrics, it's difficult to justify using those solutions in the commercial marketplace, like at banks or online vendors. So it's a complex ecosystem here. Government is getting involved now in various venues around the world. The EU, great. They're in the UK, in the US. We're seeing more pressure on building secure systems and better accounting for what we do. And that may help change the economic balance a little bit, but it's evolving. And we have to keep in mind that really the field is young and it will take some time before this all settles out.
You mentioned there the kind of legislation side of it, but while we're still in this period of effectively running around plugging holes and writing spaghetti code to fix problems that we find that we didn't anticipate we were going to find, there's always got to be that balance between convenience, practicality, and cost, as well as kind of security, hasn't there? Because you can make even modern computer relatively safe if you disconnect it from everything, but then you lose the convenience, right?
Right. And again, this comes down to not being able to evaluate the trade-offs well. If we can't measure the difference in how secure, safe, private our systems are, if we connect in a certain way, it's difficult for anyone to make a judgment about, is it worth it to me to do so? So right now, we have lots of people making that decision on a feeling that it's an acceptable kind of risk, or that we have to do it this way to be able to be in business. And if they don't know what the alternatives are and they don't know how to measure it, they can't really make a fully informed choice.
And the other thing I was thinking was, can we use existing technology to bootstrap some of these ideas, to, use some kind of machine learning system to say, right, okay, if we started from scratch, you may... the system that's designing it might not be able to run on it, almost like the blacksmith who makes the sharper tool from the sharper tool. Is that something that maybe something you are researching, or how do you come up with this specification, I suppose?
Some people are looking at that. We actually have developed techniques over the years and architectures that work well. It's a matter of, can we convince people to use them? I mentioned sunk cost as one of the issues. Probably the biggest issue we have is complexity. That because of sunk cost, what we do is add on new layers. We put in new tools, new boundaries. We move things into virtual machines. We move things into cloud environments, all in an attempt to address a certain set of problems. But what they actually end up doing is add to the complexity. And complexity is where unanticipated, unknown failures occur, where, because we don't understand whole system design well, attackers can find flaws and seams. And we have to get away from that idea of just adding more, even in the environment where we have the free software environment, or some of the new popular programming methodologies, the agile programming. None of those are really oriented towards removing old code. They're more towards adding new features. And all of that just leads to greater complexity. At the time of the Ware report, and for 20 years after, any of us graduating with an advanced degree in computing, and some who just on their own, we could teach someone else everything from the bare circuitry up to the human computer interface and how it all worked and how it all fit together. I would contend there's no person alive who can do that anymore because the systems have gotten so complex. And that means that no one really understands how the whole system works and where the problems are. So that's another aspect of the misconception, is the idea that adding more makes things better, or that patching is somehow security. Those are really enemies of security because they add to complexity.
Because what these languages are doing is they're allowing you to express a problem and a solution to the problem that you have in terms of a computer.
Working in binary.
So
Let's now, for our second counter, let's record whatever the value of the tape head is, which is either going to be 0 and 1, but we can use it.